Good day everyone, I am Joanna Grace G. Tiglao. Together with Angelica May M. Reyes, we are going to talk about the lesson number 5, AC Power 3-Phase System. First, let's go on to our lesson objectives. At the end of the topic, you will be able to first, differentiate apparent, reactive, and true power. Second, calculate power factor. Third, differentiate single and three-phase system. Introduction. In an AC circuit with reactance, the current supplied by the generator either leads or lags the generator voltage. Then the product V times I is not the real power produced by the generator, since the instantaneous voltage may have a high value while at the same time the current is near zero or vice versa. The real power in watts, however, can always be calculated as I to R, where R is the total resistive component of the circuit. In a three-phase system, the alternator with three generator windings equally spaced around the circle. The windings produces output voltages 120 degrees out of phase with each other. Now let's go on to our main lesson. The components of the power triangle. Consider an RL resistor-inductor circuit in which the current phasor lags the voltage phasor by an angle of theta. In the diagram of the circuit, the current can be resolved as two rectangular components. As we can see on the right side, there is a photo. That is the diagram. On A, the horizontal component phasor, I cos theta, and B, the vertical component phasor, I sin theta. Note that the horizontal component phasor is always in phase with reference voltage V, while the vertical component phasor is always 90 degrees out of phase with reference voltage V. We can now form the power triangle by multiplying each of the current components by the reference voltage V. The power triangle is illustrated on the right side of your screen. The three components are sides of a right triangle, and by using trigonometry, we can solve for the values of each power component. Now let's go on to the apparent power S. It is the total power that appears to be transferred between the AC source and load. It is measured in volt amperes or VA. Apparent power has two components, the true power and the reactive power. True power. The power which is actually consumed in the circuit is called true power, or it is sometimes called active power. The power is consumed in resistance only, since neither pure inductor L nor pure capacity C consumes any active power. For true power, current and voltage are in phase in a resistance. Therefore, current in phase with voltage produces true or active power. It is the only useful component of apparent power. It may be noted that it is the true power that is used for producing torque in motors and supplying heat, light, etc. It is used up in the circuit and cannot be recovered. True power has a unit measurement in watts, or W. Next is reactive power, the component of apparent power which is neither consumed nor does any useful work in the circuit is called reactive power. The power consumed, or true power, in L and C is zero because all of the power received from the source is 1 quarter cycle is returned to the source in the next quarter cycle. This circulating power, called reactive power Q, does no useful work in the circuit and merely flows in the circuit back and forth. Apparent power is measured in volt amperes reactive, or VAR. In the power triangle, the angle theta can be used to relate the power components. The power factor is the ratio of the true power to the apparent power, and it is expressed in terms of theta. If the angle theta is below the x-axis, the angle is said to be lagging. I lags with respect to the reference voltage V. While the angle theta is above the x-axis, the angle is said to be leading. It leads with respect to the reference voltage V. In the photo on your screen, it says that apparent power raised to 2 is equals to the summation of true powers raised to 2 and reactive power raised to 2. In short, S raised to 2 is equals to P squared plus Q squared. For solving the apparent power, we have S is equals to V times I. For solving the true power, we have P is equals to S cos theta is equals to VI cos theta. For solving the reactive power, Q is equals to S sine theta is equals to VI sine theta. And for solving for the power factor PF, we have PF is equals to true power over apparent power, or P over S is equals to cos theta. Now let's have an example. A motor draws a current of 20 amperes while being supplied by a 240 voltage AC source. The power factor is 0.8 lagging. Determine the components of the power triangle. For the solution, we have S is equals to V times I, so 240 times 20 is equals to 4.8 kVA. For P, we have V times I cos theta, so 240 times 20 times 0.8 is equals to 3.84 kW. And for solving the theta, we just need to do cos raised to negative 0.8. That is equals to 36.87 degrees. Now, for solving the Q, we have V times I times sine theta. So that is 240 times 20. So that is 240 times 20 times sine 36.87. That is equals to 2.88 kVAR. The circuit receives an apparent power of 4,800 VA and is able to convert it into a useful power of 3,840 W. The reactive power of 2,880 VAR does no useful work and flows in and out of the system periodically. The circuit requires an additional power I sine theta to provide for this power. Next is power factor. Power factor. The power factor in purely resistive circuits is equals to 1, while the power factor of purely reactive circuits is equals to 0. For a circuit having R, L, and C, the power factor values lie between 0 and 1. It is a useful practice to attach the word lagging or leading with a numerical value of power factor to signify whether the current lags or leads the voltage. Thus, if a circuit has a PF of 0.5 or power factor of 0.5 and the current lags the voltage, we generally write PF 0.5 lagging. An ideal value for power factor is 1, also called as the unity power factor, in which all supplied power is made into useful power. The power factor is a measure of effectiveness in using the power supplied to it, so we wish that the power factor should be as near to 1 as possible.
Hello, this is Angelica Mayam Reyes and I'll be discussing about the three-phase system. According to our module, the generator producing a single-phase supply, called single-phase generator, has only one armature winding. But if the generator is arranged to have two or more separate windings displaced from each other by equal electrical angles, it is called a polyphase generator and will produce as many independent voltages as the number of windings or phases. The electrical displacement between the winding depends upon the number of winding phases. For example, a two-phase generator has two separate but identical windings that are 90-degree electrical apart and rotate in a common uniform magnetic field. The generator will produce two alternating voltage of the same magnitude, and frequency having a phase difference of 90 degree. Ayan, makikita nyo sa image yung two-phase generator. Moving on, similarly, a three-phase generator has three separate but identical windings that are 120 degree electrical apart and rotate in a common uniform magnetic field. A three-phase generator will therefore produce three voltage of the same magnitude and frequency but displace 120 degree electrical from one another. Although several polyphase systems are possible, the three-phase system is by far the most popular because it is the most efficient of all the supply system. Sabi nga dito, yung three-phase system daw is the most popular because it is the most efficient of all the supply system. Now, the following are the advantages of three-phase system over single-phase system. In a single-phase circuit, the instantaneous power varies sinusoidally from 0 to a peak value at twice the supply frequency. This pulsating nature of power is not suitable for many applications. However, in a balanced three-phase system, the power supplied at all instants of time is almost constant. Because of this, the operating characteristic of three-phase apparatus in general are superior to those of similar single-phase apparatus. Next, the output of a three-phase machine is greater than that of a single-phase machine for a given volume and weight of the machine. In other words, a three-phase machine is smaller than a single-phase machine of the same rating. Next, the three-phase motors are much smaller and less expensive than single-phase motors because less material, copper, iron insulation is required. Moreover, three-phase motors are self-starting. They do not require any special provision to get them started. Most single-phase motors require internal starting device. Next, transmission of electric power by three-phase system is cheaper than that of single-phase system, even though three conductors are required instead of two. In transmitting the same amount of power over a fixed distance at a given voltage, the three-phase system requires only 3/4. It requires only 3/4 the weight of copper than the required by the single-phase system. This will translate into saving the number and base size of transmission towers. Next, three-phase is easier to convert to DC than single-phase. This means that radio and TV transmitters requiring DC voltage use three-phase systems that uses three-phase system. Three-phase motors have higher power factors than single-phase motor, making three-phase motors more efficient. And next is phase sequence. Phase sequence, according to our module again, is the order in which the voltage in the three-phase or coils of an alternator reach their maximum positive values is called phase sequence or phase order. The phase sequence is also determined by the direction of rotation of the alternator counterclockwise. Thus, in the figure, the three coils A, B, and C are producing voltage that are displaced 120 electrical degrees from one another, referring to the wave diagram of phasor diagram in the figure. it is easy to see that voltage in coil A attains maximum positive value first. Next is coil B and then the coil C. Hence, the phase sequence is ABC. If the direction of rotation of the alternator is reverse or clockwise, then the order in which the three phase attains their maximum positive value will be ACB. Hence, the phase sequence is now ACB. Thus, the voltage in coil A attains maximum positive value first. Next is coil B and then next is coil C and then coil B. Since the alternator can be rotated in either a clockwise or counterclockwise direction, there can be only two positive phase sequence. The three phase of winding may be number 1, 2, 3 or lettered A, B, C. However, it is usual practice to name the three phase or windings after the three natural colors such as red, yellow, and blue. R is for red, yellow is for Y. Y is for yellow, and then B is for blue. In that case, the phase sequence in RYB, thus this voltage and phase R attains maximum positive value first. Next is phase Y and then the phase B. It may be noticed that there are only two possible phase sequences, RYB and RBY. By convention sequence, RYB is taken as positive and RBY as negative. Next is interconnection of the three phases. In a three-phase alternator, there are three windings or phase. Each phase has two terminals, starts and finish. Meron siyang two terminals, which is yung start nga and yung finish. If a separate load is connected across each winding as shown in the figure, 6 conductors are required to transmit power. This will make the whole system complicated and expensive. In practice, the three windings are interconnected to give rise to two methods of connections: the star or Y connection and mesh or delta connection. In a Y connection, a common end is A prime, B prime, and C prime connects the windings. Three end lines A, B, C are connected to the junction points RYB. The common point is called neutral point or end. If the neutral end conductor is used, the system is called a three-phase or four-wire system. If there is no neutral or end, the conductor used, the system is called a three-phase or three-wire system. In delta connection, the start end of B is connected to the finish end of A. The start end of C is connected to the finish end of B, and the start end of A is connected to the finish end of C. Three end lines A, B, C are connected to the junction point of RYB. In delta connection, only three-phase, three-wire system is used. Ayan yun, yun nasa image. Next one, the last one is balanced three-phase system. According to our module again, a balanced three-phase supply system, the Y or delta connected, is one in which the three-phase voltage are equal in magnitude and frequency but displays 120 degrees from one another. The same is true with regard to line voltage. All electric companies make efforts to ensure the availability of three-phase balance supply at all times. There are two types of three-phase load: star-connected load on the left and the delta-connected load on the right of the figure below. Ayan no. Ayan yung example, yung Y-connected load and delta-connected load. The three-phase load or Y or delta-connected is said to be balanced if load is equal phase is the same. And if a three-phase load, star or delta-connected, does not meet any one of the above requirements, it is said to be unbalanced. A three-phase star-connected alternator may be connected to a Y-connected or delta-connected load. Simply, a three-phase delta-connected alternator may be connected to a Y-connected or delta-connected load. That's all. Thanks for watching.